Can you see my screen now? Yes. Okay, guys, so the last topic for today is the local area networks. Okay, so the first topic that we're going to cover is the address, in this case, which is MAC addresses. And we use a protocol for that, is called ARP. Let's look at this. So MAC addresses and the ARP, you know, guys, that we use 32-bit IP address at the network layer for the interface. And that IP address is used for the network layer forwarding. But we need another address so that we can transfer the frame from one node that is physically connected to another node. So that's why we need a MAC address. So the main function of this MAC address is to use locally to get frame from one interface to another physically connected interface. And this MAC address consists of 48-bit that is burned in the NIC card or ROM, and sometimes it's software settable. An example for a MAC address is given as follows, which is a hexadecimal base 16 notation, and each number represents 4 bits. This is a typical MAC address. Okay, and then how we're gonna, assign or determine the MAC address of a node. First of all, each NIC on the LAN has a unique LAN address. As you see, this node has a 1A, 2F, this one has a 58, 23, and blah, blah. And this MAC address allocation is governed by the IEEE organization. So like Wi-Fi or this NIC manufacturer, they purchased the portion of MAC address from this organization. So if you compare the MAC address versus the IP address, IP address is like a postal address of a home, your home, and the MAC address is the Turkish number, national number of each person living in that house, so that we can identify, differentiate each of person in a single IP address. So the MAC is a flat address. It's a portable, basically. What means portable? You can move LAN card from one LAN to another one. IP hierarchical address, not portable, if you guys remember. It depends on the IP subnet, which node is attached. Okay, so how do we determine the interface's MAC address, knowing its IP address? That's the main question that we need to address. So I have a node and I know its IP address, but how can I determine the MAC address of this node? And we use the ARP protocol for this purpose, which stands for Address Resolution Protocol. So you guys see that the IP address is 137.196.7.78, but the MAC address is given by this 1A2FBB7609AD. And the question is, the answer is using the ARP. So we have a table in ARP, which is called ARP table. Each IP node on LAN has a table, such table, ARP table. So the IP MAC address mappings for some LAN nodes. We have a column which is for IP address. The next column is for MAC address, and the third column is for time to leave, TTL. TTL is a time after which address mapping will be forgotten, and this is typically after 20 minutes. Okay, let's say in the same local area network we have two nodes, node A and node B, and node A wants to send a datagram to the node B. But the problem is B's MAC address is not in A's ARP table. So how the node A is going to learn the B's MAC address? That's the question. Using the ARP protocol. So first of all, the node A is going to broadcast ARP query packet that is going to broadcast to the whole network that containing the B's IP address using this broadcast destination MAC address. So all the nodes on this LAN network, they're going to receive this broadcast ARP query. Of course, only the B is going to reply to the A with its B MAC address. So B is going to send a frame along with its MAC address to the A's MAC address using the unicast. It doesn't have to, it's not gonna broadcast this information. It only unicast point to point to A's MAC address. Once the A receives this B's MAC address, it's saved into the IP to MAC address pair in its ARP table. And this information can live for the amount of TTL. Remember, it was about 20 minutes. Soft state information that times out, it will goes away unless refreshed. ARP works like a plug and play strategy. It works based on this strategy. So, you know, you just plug and it starts to self-learn. So nodes, they create their own ARP tables without any, feedback or input from the admin. Okay, let's look at this addressing, how it works and how we use this address to transfer a frame from one node to another node, another LAN even. So assume that we have a local area network here, the first LAN, and there are many nodes that are attached. Assume that in this case, node A, and we have another local area network, LAN. Similarly, different number of nodes are attached to this LAN, and these two LANs are connected through a router R. So the main objective here is node A wants to send a datagram to nodes B via router R. That's our objective. So in this case, we have some assumption. Assume that A knows B's IP address. Assume also A knows IP address of first hop router. We learned that. Assume that A knows R's MAC address. Based on this assumption, so let's start the frame transmission. First of all, A is going to create an IP datagram with the IP source and IP destination. In this case, IP source is 1111, as you see, and IP destination for B is 222, and this is the IP address. And then it's going to pass this datagram to the link layer, and we encapsulate this datagram and add the MAC source MAC address as well as the destination MAC address. In this case, the source MAC is CSE479, which is the MAC address of A. The destination MAC address is the physically connected adjacent router, is not the B's MAC address, okay? It's the MAC address of the physically connected adjacent router, which is E6, E9, blah, blah. So after forming this frame, we are now ready to transmit this frame over the physical link. So we transmit it, and the router received this frame, and it's gonna extract the header, datagram removed, passed to the IP address layer. So, and then it's gonna change the MAC address. We are still keeping the source and destination IP address as same. We've passed to the link layer. Now we change the MAC source and MAC destination. As you see, source is 1A23 blah blah, which is the MAC source address, and the destination now it's changed. It becomes the MAC address of the B node. And then we start to transmit. And then node B receives this frame, remove the datagram, and send to the IP layer. That's how we transfer frame from one local area network to another local area network. Okay, so one of the best and popular, let's say popular technology, sorry, is Ethernet. In terms of local area network technology, is one of the dominant, most dominant wired LAN technology. And this NIC is about $20, which is cheap. And it's firstly widely used LAN technology in the literature. Why it becomes dominant and popular? Because it's simpler, cheaper than the token LANs as well as the ATM. And it can provide a different speed from 10 megabit per second up to 10 gigabit per second. Let's look at the Ethernet topologies. There are two main topologies. The first one is bus, which was popular through the mid-90s, and because in this topology, all the nodes in the same collision domain, as you see, so all the nodes can collide with each other. And that was one main disadvantage of this bus topology. But when you look at the star topology, it becomes more popular, which is being used mainly today's technology. And in the star topology, we have an active switch in the center. So with these switches, all the nodes can talk to each other without collision. Let's look at the frame structure of Ethernet. So remember, the sending adapter NIC encapsulates the IP datagram into Ethernet frame, as you see. And we have some, this is the data payload, this is the CRC, remember, for the error correction and detection. And we have some header, which consists of preamble, destination address, source address, type, and so on. Let's look at the first field, which is the preamble. In the preamble, we have 7 bytes, which has a specific pattern, and as you see, followed by 1 byte with pattern, specific pattern again. These bit patterns are utilized for the synchronization purpose and clock rates. So the second field is addresses. You guys see destination address, 6 byte source and destination MAC addresses. So if an adapter NIC receives the frame with the matching destination address or with a broadcast address like an ARP packet, ARP query, it passes data in frame to network layer protocol. Otherwise, the NIC adapter is going to discard the frame. We have a type fields, which indicates the higher layer protocol. Of course, the most popular one is the IP protocol. In the past, we have the novel IP and we have Apple Talk and so on. CRC field is utilized for the error detection. So if the error is detected, the frame is dropped. Okay, Ethernet technology is a connectionless, unreliable protocol technology. So connectionless, there's no handshaking between sending and receiving NICs. And it's unreliable because we don't send any kind of X or NACs. We don't provide any feedbacks. If we have some dropped frames, this is recovered only if initial sender uses kind of higher layer reliable data transfer technology, such as in case of TCP. Otherwise, the dropped frame is lost. And Ethernet utilize the unslotted CSMA CD with the binary backoff as a MAC protocol, multiple access protocol. So let's look at the Ethernet standard, which is IEEE 802.3. Let's look at the link and physical layers. Many different Ethernet standards, as you see from here, but they have a common MAC protocol and frame format. Can provide at different speeds from 2 megabit per second up to 10 gigabit per second. And it can support different physical layer media such as fiber cable or other copper cable and so on. For instance, in this case, we have a 3 standard, which is for the copper, and we have 3 standard for the fiber optics. Okay, let's look at the Ethernet switch, which is a link layer device. Remember, we have the router at the network layer. And this Ethernet switch is a link layer device, and it can take an active role. So what does it do? It store and forward the Ethernet frames. How do we achieve this? By examining the incoming frames MAC address. We look at the incoming frames MAC address, and we selectively forward the frame to one or more outgoing links. In this case, we use the CSMA CD as a multiple access protocol. And it's a transparent, so the hosts are unaware of presence of switches. They don't see if there's a kind of switch between this transmission. And Ethernet switch, has a plug and play feature, and it learns these interfaces by using the self-learning method. So switches, you don't have to configure the switches. You just put it there and it starts to learn by itself. How this learning happens. So before that, let's look at this multiple simultaneous transmission feature of switch. So each host has a dedicated direct connection to the switch, as you see. 1, 2, 3, 4, 5, 6 interface. So each Ethernet protocol used on each incoming link, so that's why there's no collision, and it provides a full duplex communication. And so that's why it can provide a switching mechanism simultaneously without collisions. For instance, the A can talk to the A prime, and at the same time B can talk to the B prime, and there will not be any collision. Switch forwarding table. We have a forwarding table at the switches. So the first question is, how does switch know A prime is reachable via interface 4 or B prime is reachable via interface 5? How does switch knows this information? So the answer is each switch has a switch table and each entry consists of the following information. The first column is MAC address of host, the second column is interface to reach host, and then the third column is timestamp in this table. It looks like a pretty like a routing table. And the next question is how our entries in this forwarding table are created and maintained. Okay, we said that switch is a plug and play and it has a self-learning. You don't have to configure such device. So switch learns which host can be reached through which interfaces. So of course, when you plug into that, it starts to receive the packets, the frames from each host and start to learn from the location of the sender. And then it records this sender location pair in the switch table. Let's look at an example. Like in this case, we have the node A is trying to send a frame to the node A prime. So, and we have this switch forwarding table. So the switch starts to receive its first frame from the A. So that's why it records this location and sender information. As you see, this frame came from MAC address A through the interface 1 and TTL is 60. So switch has some frame filtering and forwarding capability. How this works is based on algorithm. One frame received at switch, first of all, it's gonna record the incoming link and the MAC address of the sending host, of course, and then index switch table using the MAC destination address. If entry found for the destination, then we have two options. If destination on segment from which frame arrived, it's going to drop frame. Otherwise, it's going to forward the frame on the interface indicated by the entry. If there's no entry for the destination, then it's going to flood. So that it's kind of a broadcast to all the interface except the arriving interface so that it can learn information. Let's look at an example for the self-learning and forwarding. Assume that node A in the network is trying to send a frame from A to A prime. So these are switch forwarding table. So it receives the frame, the switch, and it records this entry, frame destination. So MAC address, this frame comes from A through the interface 1 and TTL 60. But destination is A prime because this is the first time switch doesn't have information about the A prime. So the location of A prime is unknown. That's why it's gonna flood to all nodes except the incoming, which was A. So the A prime is gonna receive and then send a response. So now the switch has second record, which is about the A prime, and the interface is 4 and TTL is 60. So, and then selectively send to the A. So this way, switch starts to build its switch table by using the self-learning. And then we can use multiple switches to come up with larger networks. S1 can be connected to the S4, S2, S3 to create a larger network, more complex networks. So in such large network, one of the question, let's say node A wants to send a frame from A to G, but A is attached to S1 and G is attached to S3 switch, as you see. How does S1 know to forward from frame destined to F via S4 and S3? The answer is self-learning. We just give you an example. So using the same algorithm to forward from A to G. An institutional network, in such network, we have different hierarchy. You guys remember different switches. And let's compare the switch versus the routers. You guys know that the routers are at the network layer and switches are the device at link layer. So both, the main function of both devices is to store and forward, right? So the router, they store and forward the datagram. The switches, they store and forward the frame. How do we achieve this? By examining the network layer headers. So the routers look at the header of the incoming datagram, and the switches, it examine the link layer headers by looking at the header of the incoming frame. And both have a forwarding tables, as you see, and routers compute these tables by using routing algorithms. Of course, in this case, we utilize the IP addresses. But on the other hand, switches learn forwarding table using flooding or the other self-learning that we just learned. And it utilizes the MAC addresses compared to IP address at the network layer. So these are the main differences and similarities between switches and routers. Okay, last topic for today is called virtual local area networks, VLANs. So let's look at the motivation behind this concept. I mean, why people come up with this such concept. Let's consider a case that, university, we have different departments like computer science, electrical engineering, computer engineering, and so on, different departments. So assume that there's a computer science user that moves office to the electrical engineering building, but still wants to connect to the, computer science switch. In such case, you cannot move the switch, whole physically to another building. So we need to come up with some virtual solution. Single broadcast domain. So all layer 2 broadcast traffic, including the ARP, DHCP, must cross entire LAN. And another is because of the security, privacy, efficiency issues. So that's why people, they come up with the VLANs. Okay, so let's look at the VLANs detail, virtual local area network. First of all the switch doesn't have such features, so the switch that has a VLAN capability can be configured to define multiple virtual LANs over a single physical LAN infrastructure. So one of the approaches is called port-based VLAN. So in this case, as you see, this is a 16 port switch, as you see, and we split into two groups this port. The first blue group is for electrical engineering, VLAN ports from 1 to 8 is assigned to the electrical engineering department, and the remaining from 9 to 15 are allocated to the computer science. As if we are splitting these physical switches into two small 8-port switches, right? But we are doing this virtually. So in this port-based VLAN, let's look at the traffic isolation. Frames from ports 1-8 can only reach ports 1 to 8. So you isolate the traffic of electrical engineering from the traffic of computer science. So we can have some dynamic membership in this VLAN. So the port can be dynamically assigned among these VLANs. For instance, this third port can be assigned to a computer science group. And forwarding between these different virtual LANs can be done through the routing or router device. In practice, the manufacturer, they sell a combined switch and the routers in a single box. Okay, you can span these VLANs over multiple switches. Like in this case, we have two switches. One of them is 16 port, the other is 8 port. Two physical switches, they are separate. And then you can assign different user to the different switches to create the VLANs. For instance, in this case, this was in the previous example, second physical switch. We assigned the 2, 3, 5 ports to the electrical engineering VLAN, and the 4, 6, 7, 8 ports are belong to the computer science VLAN. But the question is how we are going to connect these two physical switches is using the trunk port. The red line is called trunk port. It carries frames between the VLANs that is defined over multiple switches, physical switches. So the frames forwarded within VLAN between switches cannot be vanilla, the normal frames. So instead we use a 802.1q protocol that adds or removes the additional header information for frames between the trunk ports. What are the main difference? As you see, between the vanilla and the 1Q frame is some additional information in this field. As you see, is a 2-byte tag protocol ID, tag control information, which shows the 12-bit VLAN ID field, and 3-bit priority field like IP toes. All right, guys, that's all for this chapter. Any question? Any question?